All right. So we're going to continue our conversation that we had yesterday with the upper and lower sums, but we're going to give it a better name and talk about different strategies we can use. So what you guys were working on yesterday is something called Riemann Sums, named after Georg Riemann, who I'm pretty sure was German. Yep, German. So, some people pronounce Riemann differently. I'm just saying it the way I heard it. If you guys hear different, let me know. All right. So, we're going to find the area of the region bounded by the graph. F of x is equal to x cubed plus 2, the x-axis, between negative x equals negative 1 and x equals 5 using 3 equally spaced intervals. So, again, first thing I just want to make sure you guys understand is what you are doing is you're trying to estimate the area under the curve, aka you're estimating what the definite integral is. And we call it definite integral because we are starting at x equals 1, we're going to x equals 5, and we're trying to estimate the area underneath that curve. All right? So, mathematically speaking, they're asking us to figure out this right here. Integral. We're starting at negative 1. We're going to 5. So the lower bound, or the lower limit, I guess I should say, is negative 1. The upper bound is 5. We are talking about the function x cubed plus 2 with respect to x. That's what they're asking us to do. I just want to make sure you guys are comfortable writing that notation out. Okay. So to do this, we need to create a visual of this graph. So, let's get drawn. First, I'm going to start off with my axes. All right. And I'm going to go ahead and, because I remember what a cubic function looks like, the plus 2 just moves it up 2 spaces. So I know that it should look something like this. Right? But let me do a better job because we're going to need a little more of the graph to answer this question. So I'm going to scale it down a little bit. All right, it's going to go off like that forever. That's kind of what my graph looks like. So I'm going from x equals negative 1 to x equals 5 in 3 equally spaced intervals. And if you notice, we talked about the left, the right, the midpoint, and the trapezoidal. So I'm going to show you how all three work. Left and right is very similar to what you were doing yesterday. So hopefully this doesn't take too long to explain. All right. So let's zoom in on the graph. Okay. We're going to start at x equals negative 1, 0, 1, 2, 3, 4, 5. So 5, 1, 2, 3, 4, 5. Okay. So I'm just kind of skip counting because I don't want to write all those numbers since I'm going to have to use this graph. So they're asking me to get the area from here to here of that graph. All right. And so I'm going to extend this graph a little more, kind of get it to meet. Okay. So that part underneath the curve, bounded by the x-axis between these two x values, that's what I'm looking for. So let's go ahead and start talking about these Riemanns. All right. So the first thing I need to do is I need to break these up into 3 equally spaced intervals. So since I'm going from negative 1 all the way to 5, there's a difference of 6. between those two values. So if I break that into 3, I need to count by 2. So from -1 to 1, from 1 to 3, and then 3 to 5, equally spaced. So as the name suggests, we're going to talk about the left Riemann sum. So from the left side, we're looking at what if I draw my rectangles coming in from the left and using that as my starting off point for the heights. So if I do so, I need to figure out this, draw it over, this, draw it over, this, draw it over. So very similar to what we were doing yesterday. So at this point, you should know that I need to figure out the height, because since I'm using a rectangle, it's base times height, and I know that the base will always be 2. So I just need the heights, which are found by f of x, which is x cubed plus 2. Okay, so if I plug a 1 in there, -1 cubed is -1 plus 2 makes it 1. So it'd be 2 times 1 plus 1 cubed is 1 times plus 2 is 3. So 2 times 3 plus 3 cubed is 27. 27 plus 2 is 29. So 2 times 29. We do our calculations, that spits out a number, and that's what our left sum should be because we determined the height from the left side. If we take the same idea, but now we talk about the right side, I can keep pretty much the same numbers I have. I just have to look at it from another side. Right? All right, and if we're coming in from the right side, now I'm starting from the right side to determine the height. So for the first one, I would start at the 3, bring it down and over. 29, bring it down and over. This one up here, bring it down, bring it over and down, I should say. Right, so for this new one, I'd have to plug that 5 in. 5 cubed is 125, so this should be 127. So I have my 3 rectangles to get the area. Again, it's just base times height. The base is 2. The height for the first one would be 3. The height for the second one would be 29. And the height for the last one should be 127. Okay. So we can see that the left is going to give us an underestimate because if you go back to the visual, we didn't include parts of the graph. If we look at the right side, it's an overestimate because we're including parts that are not in our graph. So now let's talk about the midpoint. So for the midpoint, we need to look at a point, as the name suggests, midpoint, so halfway between the two heights that we have, and we have to use our function. So let's make that green. So midpoint would be going up here, then drawing it out like that. Midpoint's going here, going that way, and going that way. Midpoint is up here, going that way and down, that way and over. All right. So if we talk about the midpoint estimation, all I'm doing is just finding the midpoints. Instead of using -1 or using 1 as my x value, I would use 0, 2, and 4 this time for my heights. So 0 cubed plus 2 would make that 2 for the height. So it'd be base of 2 times the height of 2 plus base of 2 times 2 cubed is 8. 8 plus 2 is 10. So 2 times 10 plus 2 times 4 cubed is 64. 64 plus 2 is 66. 2 times 66. And again, for all of these, I'm showing you how to create the formulas because I don't think you need me to show you how to evaluate these estimates for the heights. All right. So if you notice, the midpoint is, in this instance, kind of nice because it has some parts that are under the curve, some parts that are not under the curve. So it's a little bit of a better estimate than the left and the right side. Okay. So we need to talk about the last one, which is the trapezoidal version of Riemann sums. So let me set up again. All right. So for the trapezoidal, we need to go back here. But rather than using rectangles, we're going to use trapezoids. So here's the way that the trapezoid is going to be oriented. Typically, when you think about trapezoids, it's the top and the bottom are the parallel sides, and the distance between them is going to be the height. We're going to go ahead and we're going to just rotate that 90 degrees. So the trapezoid will look something like this. Right? So this will be our base 1, this will be our base 2, and now this will be the height. Okay? So let's go ahead and let's use purple for it. So I'm going to go ahead and draw it out. That's one trapezoid. That's another trapezoid. And that's my last trapezoid. So one trapezoid here, one trapezoid there, and then one last trapezoid here. So notice how some of these other methods may look like they're producing better estimates, but they're also a little more work because now we have to use the good old area of a trapezoid formula, which is area is equal to 1/2 base 1 plus base 2 multiplied by height. All right. So if I use that, and I'm going to have to keep adding that, I'm going to go ahead and factor out what they're all going to have in common. All the trapezoid equations will have the 1/2 and they'll all have the height. So it's going to be 1/2. If I can write the 1/2 properly. 1/2 times 2, because the height is 2, and all I'm going to write inside the brackets are going to be the sum of the two bases. So let's get cracking. For the first one, we have right here, we're going from 1 all the way to 3. So base 1 is 1, base 2 is 3. Then that would get multiplied by the 1/2 and the 2 here, because that's the height. Plus, and the next one, we'd have the 1/2. But now we're starting at 2, going all the way to 29. Still have a height of 2, so that's why we have the 1/2 times 2 out in front of all of them. Base 1 was 3. Base 2 was 29. Plus, last one is we're starting at 29, going all the way to 127, coming all the way down. Still have a height for a trapezoid of 2. 29 plus 127. Okay? So if I evaluate all of these, I should get estimates for what I believe the areas underneath the curve should be, aka what the value of the definite integral should be. So tomorrow, when you're working on this via Khan Academy, when they ask about left, right, midpoint, or trapezoidal, that's what they're going from. Ideally, the intervals are equally spaced. But if they're not, then that just means you have to be careful with how you're finding the areas. So, for example, the trapezoidal one, I was able to put the 1/2 out in front and the times the 2 because they all had the same height of 2. But if they weren't all equally spaced, I would not be able to kind of factor out that 1/2 height that they all had in common. All right. So just be careful. These are ready to be typed in the calculator. So if you're curious about what this area could be, go ahead and type those in just to get some estimates. Good luck. There's also a second video talking from Khan Academy that'll show you how to get it from a table.